3, 2, 1, and we're live. No, I'm just kidding. Yeah, we don't really need to do this, but hey, this week, we just want to let you know that we're talking about quantum mechanics, specifically quantum, basically the history of quantum mechanics. Yeah, the history of quantum mechanics, and we talk a little bit about how Einstein was frustrated with it, you know, the field in general, because he honestly didn't like quantum mechanics.
Yeah. He was a hater.
Yeah, he was a hater. And dang, what else? What else did we cover?
We covered De Broglie, a little bit of history.
De Broglie. Yeah. He was one of the crucial ones.
Yeah.
Who else? Planck. Oh, yeah. Planck was like huge.
Yeah.
We also talk a little bit about. Come on, we had to mention Schrodinger if you're talking about the history of quantum mechanics. You know, we kind of like try to create a layman's sort of intro to quantum mechanics for dummies.
So it should be understandable.
I hope. If we're not, then, you know, leave us a like, you know?
Yeah.
If that makes any sense. I hope that kind of, you know.
And just make sure you guys subscribe to their channel.
Oh, yeah.
And then check us out on Twitter at Eigenbros.
Yeah.
And then we also have the audio on Apple, Spotify, Google Play. And yeah, that's it, guys.
Yeah. Enjoy. From me, Juan.
And Terrence.
Yeah, a.k.a. Black Aristotle, and you can just call me JJ, you know, it's cool. I'm cool with that.
All right, guys.
But yeah, guys.
We're rambling.
Hope you like the show. Peace. 3, 2, 1, and we're live.
We back, baby.
Yeah. Whoa. Damn, my levels are... Shit, I can't scream into the mic.
Yeah, don't scream in the mic.
Yeah.
But yeah.
So...
Welcome back, ladies and gentlemen.
Let's get right into it.
Well, let's first do some things here first.
If we did our job right, we should have already front loaded.
You want to front load it?
We already front loaded, baby.
Okay.
We're gonna get right into it.
All right, let's do it. So on, I guess we're here to talk about today just a brief intro to quantum mechanics and wave particle duality.
Yes.
So these are kind of these cool topics that, you know, people really don't get a chance to understand, you know, outside of the physics community.
Yes.
And since we're going to be having a podcast eventually on quantum information,
yes,
I wanted to do kind of a intro to quantum mechanics.
Mm-hmm.
Layman friendly, no math, so don't be scared. Don't shut it off.
Yeah.
We're going to try to be as understandable as possible.
Yes. This is basically intro to quantum mechanics for dummies like me.
And me. So actually what got me prompted on this was July 14th is actually Bastille Day in France. And I was just looking up holidays randomly just to see what was happening in the world. And yeah, Bastille Day is apparently the anniversary or the celebration that the French people do for the French Revolution. And, you know, all that shit went down with the bourgeois, you know, I think it was maybe Louis the 16th or something. I can't remember exactly. You know, it was bad times for the French people.
Sure.
So they were, you know, up in arms to storm the Bastille, and now it's a national holiday. And,
yeah, let them eat cake, right? That kind of thing.
I'm not sure.
I'm kidding. I don't think it is.
Okay, I don't want to quote history because I really suck at history. But yeah, it wasn't good times.
Yeah.
And and then that got me thinking about French influence on physics. And, you know, we've had a slew of, you know, great mathematicians and physicists who are French.
Yes.
And it immediately made me think of Joseph Fourier, who is kind of the father of, you know, modern, so much modern stuff because it has to do with waves.
Yeah.
Fourier was the guy who basically figured out that you can decompose any kind of wave into very simple sine waves. So that's SINE.
Correct.
You might remember it from school. They're these very simple, you know, curvy waves that everybody's seen in algebra class. And he figured out a way to decompose all kinds of waves into that, those sine waves. And then, of course, there's other French physicists, and I guess the main one who is, relevant to our discussion today is de Broglie.
So a lot of physicists even call him de Broglie.
Yeah.
Inaccurately.
So his name is spelled Debrogie. It's French, so it's Louis de Broglie.
I see. There you go.
Fucked up.
I fucked up.
So yeah, de Broglie, and he is a really important figure in quantum mechanics. Do you know anything about how quantum mechanics actually started one?
Yeah. I mean, de Broglie, he has an interesting background actually. But we can kind of he is one of the founding fathers, so to say, of quantum mechanics. Einstein is really at the forefront of that.
Right.
He won the Nobel Prize because of, sort of, if you want to talk about it in layman terms, but it's the work function.
Yeah.
And it's something that you get when you shoot light at, say, a metal. It basically ejects a particle. So yeah, in this discovery, what Einstein found was that as he shoots light into I believe it was a metal.
Yeah, you're right.
It you get an emission of a particle, and that was like fascinating at the time.
Right, but even more fascinating is the fact that Einstein, let's say, in one of the experiments, he actually shone weak blue light on the metal, and the particles still got ejected. And the way they tested this was the particles were electrons. And for those of you who are not familiar, electrons basically create current. So just like electric current, if you stick somebody in the light socket and you see the static electricity, that's from
the flow
current
of electrons.
Yeah, the flow of electrons makes electricity, basically. And when you shine blue light on this metal that he used, you would actually get a current. So that means that the electrons were getting shot off.
Right.
But interestingly enough, when he shone red light onto the metal, nothing happened. So, and then he cranked up the brightness.
So we'll say this.
Yeah.
So what differentiates red light from blue light is what's interesting is that red light has a property of having a longer wavelength, which means in the scheme of energy, if you look at the math, if you want to look at the math, but there's a relationship that says things with a certain wavelength can have either greater energy or lower energy. In the case of red light, it has lower energy.
Right.
Yeah.
So red light's kind of on the low end of the visible light spectrum for energy. And then blue light's kind of on the higher end for the visible light spectrum.
Correct.
So I know most people have heard of Roy G. Biv. It's red, orange, yellow, green, indigo, violet.
Yes.
So in that order, red goes from low energy to violet being the highest energy. And that's the order of the wavelengths. And if you go up those color scale, you're going up in energy or frequency.
Yeah. So basically, he differentiated in the light he used, right? He said, I used blue light and red light to see.
And that's kind of weird, though. The whole weirdness of this was that the fact that he shone a bright red light, like the thing is, he cranked the power all the way up, right, on that red light, and still nothing was happening. So then what the conclusion came was that you needed certain energies to be able to actually knock electrons off of this metal plate. So it turns out that what could you say? The energy levels for this is proportional to the frequency of the light. So frequency is related to wavelength. They're inversely proportional, which just means that, frequency is equal to 1 over the wavelength for a little bit of math for you there. So it means that when frequency goes up, wavelength goes down.
Exactly.
And yes, that's pretty interesting. So then that's also how they came up, I guess, with the general equation.
Yes.
Where energy is equal to, some constant times the frequency.
Exactly.
So it's a very simple relation, and it turns out to be really nice.
It was really powerful, at the time.
And one of the cooler things that yielded was the constant is actually Planck's constant.
Yes.
So I don't know if people have seen Stranger Things 3 yet, but
really?
Yes, Planck's constant kind of had a debut.
Cool.
In there. Have you not seen it
No,
yet?
I haven't seen it yet.
Dude, you got to watch it.
Okay,
it's
I'll
great.
try to find some time in there. But yeah, fuck yeah, that sounds cool.
Yeah, they had it played a pivotal role in the series.
Oh, okay.
Yeah. I won't spoil it because it's still kind of new.
Yeah.
But yeah, Planck's constant. This is the constant that's relevant.
So tell us a little bit more about Planck's constant, actually. So now that Einstein developed he discovered that, electrons have this property or light, and when it hits materials and it ejects an electron, they have this sort of relationship with the energy and the frequency.
Mm-hmm.
And it's linear on a sense, right? So it's like,
right.
So where does Planck, he comes in when? Before, I imagine? Yes. I will say yes, because I
forgot.
It's a leading question, but yes,
yeah.
he did. This is what they call it's like the quantum conundrum is what they called it, right? Because this is where black body radiation comes from.
Right. So basically what Planck did was he kind of used in true experimental fashion just a way to figure out how to make an equation for, I guess, figuring out how energy and frequency were related. So let me remember a little bit. So
he has the distribution. He had like a distribution of sort of curves, and at the time, what they were measuring was radiation, I believe, right?
Yeah.
And so what radiation is just a form of energy, if you want to get fancy, physicists like to differentiate.
You can usually fall back on anything's a form of energy.
yeah. But in this case, it really just is. And and what they found in this distribution, it didn't take a sort of classical approach. Like when the physicists were trying to really apply what they knew to this problem, using their given knowledge, they could not fit the models.
Right.
And they were having such a hard time, and a lot of them were just like, fuck it. We're just experimentalists. Let the fucking theorists figure it out.
Right. So basically there's a distinction between the classical realm and the quantum realm.
And this is almost the crux of it.
Right.
Like this is where
this is where that distinction really came to life. Yeah. So they noticed in their equations that, like Juan was saying, the classical models that they developed, and classical is like our everyday experience, when we're walking and living in our normal environment, pretty much every kind of physics interaction is classical. Of course, it can get more complicated if you're looking at like your smartphone and things, because now we live in a age where we can harness quantum capabilities.
Yeah.
But just like imagine if we're just walking in normal everyday life, you're going to be mostly dealing with Newtonian or classical physics. So then they had this black body radiation that they
called it a
measuring.
Black body.
And so a black body is basically just a body that can perfectly absorb light.
Not African-American body.
Yeah, so it basically absorbs all light.
Yeah.
You can actually fashion these things in real life too, because I think they made black bodies where you have like a cavity. So like imagine if like you just have like a empty can or something, and it's got a tiny hole in it.
Yes.
If you shoot light in that tiny hole, basically the light bounces all in the hole to where it's going to absorb all the light. And that's kind of what a black body is. And if it ever radiates outward, then you can get every single, you can measure that radiation because it's coming from the hole.
Yeah.
So black bodies can kind of exist. They're not, of course, perfect.
Yeah.
But you can kind of make them in a rudimentary way. And they're very simple to kind of conceptualize.
It's something that traps all the energy.
Yeah.
Right?
Yeah.
That doesn't come out.
Yeah, but whatever about this black body radiation, I don't really know the details. Planck basically made an equation that from just by observing, like he didn't know what it was.
He literally was like fitting. So you have your experimental data. This is literally what happened to Planck. I remember reading about this, but the paper, there's also some knowledge. If you go back to the paper's probably out there somewhere.
Yeah.
And it's probably really famous actually. But what you'll see is that they went through iterations. So they were like, yeah, we saw this, but when we fit it with this model, it fits perfectly.
Right.
And then we get this constant.
So this is actually a thing that physicists really do. You guys, for people who are not familiar, might think that, these physicists are just, coming up with these brilliant concepts in their mind and then refining it in this, nice diamond that comes out all perfect and flawless. Yeah. No. Experimentalists, a lot of times, even theorists, you just come up with an equation. Like you see certain patterns. So if you're taking data, imagine if you're measuring something and then you're just plotting that data like in Excel. You'll eventually see some pattern, and then you can try to fit an equation to it, which is just basically like drawing
y equals mx plus b. You guys remember that shit?
Yeah.
Everyone here has taken that.
Right. So if you know algebra, you know that just the straight line y equals mx plus b, that's a linear relationship.
Yeah, exactly.
And that's exactly what he found was the case with energy and frequency. I believe was that the equation he came up with, the black body equation?
Pretty much, yeah. He pulled out the constant from this.
Yeah.
And he was like, holy shit. This like fits it perfectly.
Right.
And yeah.
It's Planck's constant.
Yeah.
So that's how it became known.
And then Einstein, I guess if you want to be precise, it showed up in his equation as well.
Yeah.
Yeah.
So Planck's constant is a very critical and important constant.
Yeah.
And
it's quantum mechanical in nature.
Right.
Because the problem is like the classical models collapsed, meaning they just couldn't fit the models properly. They tried to put those equations in the data that they had, and it just didn't look. It looked like shit. It didn't look good. They couldn't coincide, and so they had to come up with new models, which in a sense is new physics. So.
Exactly. So this is like the beginnings of quantum mechanics.
Yeah.
And the reason it's called quantum is the fact that it's quantized. So the fact that you have this relation energy equals Planck's constant times the frequency of your light, it shows you that there's some minimum, what would you say?
Minimum packet or quanta
minimum
of energy.
Packet. And actually Einstein's experiment was really the one that proved this.
Yes.
The photoelectric effect, it proved that light was quantized because electrons would not get knocked off if there wasn't enough energy. There had to be some threshold.
Exactly.
And if you were above the threshold, the particles would still leave with the same energy. So it means that there's a quantized or discrete energy associated with each of those particles.
Yeah.
Which kind of leads you down the road that physics at the smaller scale is quantized. And that's how Einstein actually got his Nobel Prize, I believe, right?
A lot of people think it's for his contributions to general relativity, but this was really it. This opened up the whole field, and this was around early 1900s, actually.
Yeah.
When this data started coming out, and quantum mechanics was just burgeoning. And then here comes de Broglie.
Right. So
this new young physicist, right? He actually didn't. What's funny is, science at the time was a rich guy's endeavor usually.
Yeah.
And so with
de Broglie came from a kind of royal family, I think. Yeah.
He did. Yeah. He came from a royal family. His brother was a physicist.
Yeah.
And his brother got him to join physics, to actually start doing physics.
Because he was like a history degree or something, I think.
De Broglie?
Yeah.
Yeah.
He was a history guy.
He was a man of the arts. He was a man of culture and stuff. So he funny enough, he said, fuck it. I guess I'll do physics. And he got tutored and everything. But that shows the brilliance of it, really. But at the same time, he when he was doing his PhD thesis, he looked at Einstein's work because it was popular. The paper that he published was getting a lot of recognition, I believe.
Yeah, you're right.
And then, because it was in response to Planck's, radiation catastrophe thing.
Yeah.
The whole fiasco. And so he looked at these two sort of limits or the edge of their knowledge at the time, right?
Mm-hmm.
They looked at these two big things, throwing the middle finger to classical physics and saying, fuck you, you guys, we don't know what the hell's going on. So he used this and he combined these two papers to come up with an idea that maybe all matter has a wavelength.
Right.
Yeah. So maybe not just light, maybe all matter has this property.
Mm.
Yeah.
And that was kind of something that I guess nobody thought about before.
Yeah.
And
I mean, who would, on paper, it seems kind of ridiculous, right? Matter having a wavelength.
Right. You don't think of it like that because you're just like, you don't see it.
It's not intuitive.
Life, right? Yeah. It's not really intuitive. But he actually guessed correctly. And I think the first experiment to confirm it was they shown like electrons through a nickel lattice or something, and then proved that so basically, let me explain this. So the experiment that confirmed that matter also was a wave was they shone electrons through a nickel lattice. So if you imagine this, imagine a bunch of particles that are side by side in a nice array.
So all nickel atoms. So if you look at the periodic table, there's like nickel. You pluck those bad boys out. You put them all in a nice little box. You know, let's make it 3 particles. 2. Fuck it. Let's just make a two system or 4 particles of a cube. Yeah.
And then there's a space between each of those particles. Mm-hmm. And you can consider that as like a slit. So there's a very famous experiment called the double slit experiment, where if you shine light through a double slit, you get an interference pattern. So what that means is you get a canceling effect at certain regions when you shine light through two really thin slits. Mm-hmm. And they produce this pattern of like a light fringe. They call it a dark fringe, a light fringe, a dark fringe, and it keeps repeating. And this is a clear pattern for if you have some kind of wave that's entering through the slits. And then the way to test if it's a particle is when you send it through this double slit, you actually get just this randomized assortment of a bunch of different locations where the particle hit.
Yeah.
So the light can just go anywhere. So that's how you know it's a particle. So this is really a famous experiment that...
Yeah, it should look... Because if a particle was just a particle, you would see kind of like... If you can imagine that you're at the beach one day, right? You're sitting at the beach, you're chilling, having beer, margaritas, whatever.
Yep.
And you decide to just do your own little experiment. You take sand, right? You hold it in your hand and then let it fall in the... Sort of let it fall in between the slits in your fingers, right? So it falls down. What they do is that they pile up on each other.
Yeah.
But even if you do this, even if you just grab a handful of sand and you just drop it from your hand, it just all piles up on something. So you can idealize your hand making a small hole. Particles behave this way, right? They should just kind of plop down. They should all just fall down and make like a little cone. So we as physicists at the time, we thought, fuck, this should also be true, right? Yeah. We should see this behavior if it's classical.
Right.
But what did we fucking find, man? What did we see?
Right. So, spoiler alert, it's not. So, the electrons, when they went through this tiny slit of this space between the nickel atoms, they found that it produced an interference pattern like the waves.
Which is only a phenomena that we see in waves.
Right.
That's
so
really, That fucked us up.
Right. So that confirms that basically it's saying that electrons are wave, but we know that's not true because you can actually weigh electrons. I think, what's the guy who did the atomizer? Millikan?
Millikan.
Like, I think Millikan was the one who first weighed him. Maybe not. Maybe he just got the charge.
Yeah.
But
I think you're right.
But somebody found a way to weigh the electron, I believe, at that time. Maybe not. I think they did because I think they somehow knew it had mass.
To an error of... Maybe it had a bigger error bar, but yeah, I think you're right. I think they had some idea of what it was.
Yeah.
Nonetheless,
yeah. So they saw that these wave properties existed for electrons as well as not only just photons, but also electrons.
Yeah.
So then the other thing is to prove like, okay, then is electron a particle too? So what you do is you do the same double split experiment, but if you observe that particle before it goes through, then you get the particle pattern once again, where it's just this random pattern that has no interference.
Yeah.
Yeah, so then it's pretty much confirmed. And de Broglie was, I think he got a Nobel Prize for that, I'm pretty sure.
Yeah.
And then that kind of, these three things, Planck's constant, Einstein, de Broglie, they kind of ushered in the quantum era with these experiments.
Yeah, 3 simple experiments. But you have to think about it at the time, especially Young's double slit experiment is probably the most replicable.
Yeah.
Because all you have to do is find a slit that's on the order of, you have to think about wavelength and light and stuff like that. And you have to think about like on the order of the wavelength and stuff to get diffraction. This is for something. You can Wikipedia if you have a little bit more interest in what I just said. But nonetheless, like you could even replicate this experiment in your own home if you wanted to. Young's double slit. And so everybody was trying to confirm this because we had just seen Einstein and Einstein just say, this shit is particles.
Right.
And then Young is like, no, this shit is waves, bro. I'm saying, yeah.
And then it's kind of crazy because they're both like right in certain scenarios. And you can actually prove that light is a wave in your own home. I've done it before where just shine a flash. So you get a flashlight, and then let's say you have 2 pieces of construction paper. Just make the separation between the construction paper smaller and smaller and smaller. Eventually, when you get a really thin slit, you'll see that the light actually begins to spread out.
Yeah.
So that's a sign of something that's a wave.
Yeah.
If it was a particle, you would just get a thinner and thinner slit until it disappears.
Yeah.
But with light, it actually gets more and more spread out.
Yeah.
And that actually has to do with Heisenberg's uncertainty principle.
So Heisenberg comes in and he's like,
and he's kind of the next layer for quantum mechanics.
He's like, just fuck me up. He literally, everybody, at this point, Einstein was frustrated because once Young's double slit experiment came in, it started muddying everything up because at the time, Einstein was like, oh yeah, particle, everything's like a particle, then it kind of behaves classically. You can think about it, it's just a smaller ball.
Right.
But then Young is like, nah, man, it's, things behave as waves as well. In certain experimental setups, you can get these particles to behave as waves. So Heisenberg.
And then Heisenberg, I guess, steps in. So Heisenberg basically says a relation where you cannot measure the momentum and the position of a particle at the same time with absolute precision. So you can either know the absolute position of the part, or did I say absolute, not absolute precision, with absolute
precision.
Precision. That's what I meant to say. So you can either know the position of a particle with absolute precision, or you can know the momentum of a particle with absolute precision, or you can have a hazy understanding of the position and the momentum. You can never have both understanding of where the particle is and the momentum on the quantum scale.
Yeah.
So that is another key ingredient to quantum phenomena. And that has to do with the wave-like nature, the wave-like particle nature of quantum particles.
Yes.
Yes.
And it's sort of a limitation on it's, and here's the thing, it's not something that was made, like Heisenberg just didn't say, I have like a fucking tome, like he was God and said,
right,
you shall not break these rules. Like it's not, it's literally something that he observed. He was like, I can't measure the position and the momentum at the same time. And momentum, just if you want to be fancy, it's just velocity with an M with mass attached to it.
Yeah. So you can just think of it as speed. You can't measure the speed of a particle and
the position at the same time.
With absolute precision.
Yeah, think about this in your everyday life, right? Compare and contrast to that, and you'll see kind of how funky that is. But yeah, and it was shocking to the world of classical physics thinkers like Einstein, because he was like, he had a problem with it actually.
Yeah, because it doesn't make any sense.
Yeah,
it just defies all intuition.
Exactly, and but Einstein was one of these like realists. He believed that the wave nature was due to our own limitations in some manner. So he pretty much at this point was kind of done with quantum mechanics and was like trying to prove that it was not this ridiculous.
Right. Him and Schrodinger would come up with, well, I think mostly Schrodinger came up with Gedanken experiments, which is just means thought experiments.
Exactly.
And they would try to find ways to try to
counterexample,
show the ridiculousness of quantum mechanics.
Yeah.
Or just where there's holes. Of course, the most famous is the Schrodinger's cat, right?
Yeah.
And that's just basically saying, just a quick summation is,
you've probably heard it 1,000 times at this point.
If you put a cat, but for people who haven't, you put a cat into a box with some kind of radiation in a bottle. And if
quantum mechanics says is that the cat is in a superposition.
Well, you're kind of jumping the gun.
Okay. You want to give him the physical picture first.
Yeah, the radiation. So the thing about radiation is, if you have some kind of radioactive atom or something, right? It can decay, which just means it releases some kind of like alpha particle or something. An alpha particle is just a
high energy.
Yeah, just some kind of particle that releases
a lot of energy
from something that's unstable.
And that energy, when it hits randomly, when that energy hits you, it damages the cells on your body, gives you cancer. So stay away from radiation, kids.
Yeah, but alpha particles are probably the best one to get hit by. You just don't want to get hit by like gamma rays.
True.
Or something. Or maybe like even X-rays.
Yeah.
Too often. But yeah, so what happens is you have the radiation in this box, right? And then the radiation is set to trigger like a hammer or something, or a gun or something. Maybe not a gun, because then you'd hear it go off, but something to kill the cat.
Yeah.
And
the example was like a poison vial.
Yeah, poison vial. So if you put the cat in this box and then close the lid, you do not know if the cat is dead or alive. It's in this undetermined state. And the only time you'll ever know that it's dead or alive is if you open the box.
And this is because the radioactive process is quantum mechanical in nature.
Yes, exactly.
And this is why he was so perplexed by it. He was like, you're telling me that I can make this experiment. The thing is, he could have done this experiment, but ethical issues aside,
right?
He could never really fully go through with it. But he was saying the absurdity of that moment is that I can't fucking figure out if the cat is dead or alive at any given moment up until I open the box.
Right.
Up until I observe directly what's going on. I can't tell you with like any real precision. And physicists and scientists specifically, we want to describe the world with some degree of certainty. So we were obsessed. We were obsessed with, we come from this classical sort of point of view where we want to describe everything with a high degree of certainty.
Yeah.
Because we're used to that. It's nice.
And one interesting thing about this experiment, is the whole thing with the undetermined state versus the superposition. So we were talking about this earlier, but
so superposition, we're not really going to define it just yet, because we are going to try not to give you the wrong impression of what it is. For now, we're going to use it as most physicists, I guess, describe it. Right?
Every physicist says the superposition is a combination of in a 1 or a 0 state.
Yeah.
This is not really a satisfactory way of saying it to me personally, although the math describes it like that. Yes. But nobody really knows what that means, right?
So it's a unique property, at least the way I like to think about it, is a unique state of like
being
of physics where a particle can be in said superposition.
Yeah.
And all it means is that you have the particle has certain available states of being.
Yeah. So imagine the cat again. The cat is dead or alive. So dead would be 0, alive would be 1.
Yeah.
So it's in this mixed state. It's either dead or alive, but superposition specifically says it's in some kind of combined state.
It's in both. The math says that it's in both.
The interesting thing about this is there's like two ways you can look at this. You can say, okay, as someone who just is a logical thinker, you're just like, okay, this just means that it's in an undetermined state. So the cat is either dead or alive. It's not determined. It's not actually in a weird mixed state. It's just you don't know what it is. So if you open the box, you'll know what it is. It's in some state. You just don't know what it is. But in the other hand, with quantum actually says it's in some mixed state, some distinct state other than being in an undetermined state. It's in a superposition. So superposition and undetermined are two different states.
Yeah, so you thought you could slip out of that one, right?
Yeah. And this is what Einstein had a problem with. He called it hidden variables, basically. And the thing is, it was actually disproved by Bell, I think. It's like
This was in the 70s.
Yeah,
Bell,
some Bell inequality experiment or something.
yeah, he came up with this sort of thought experiment. It's a thought experiment as well. And but he used math.
Yeah.
So he got a little bit fancy, and he was like, actually, this says that if you want quantum mechanics to be true, I'm going to have to violate your worldview a little bit.
Yeah, so it was interesting because the conclusion he came up with was an undetermined state actually yields different probabilities when you measure your state. So measuring the state in this case would be opening the lid for the cat.
Yeah.
As opposed to the superposition, you actually get different probabilities, which is like, imagine this, if you flip a coin like 20 different times, eventually you're going to get 50%. You're going to get a distribution of 50% heads and 50% tails. Let's say if you do it enough times. With this, if you open up the lid for the cat enough times, you're going to get a certain probability distribution that is different than the undetermined state. So this proves that the mathematics of quantum mechanics holds up for this system, whereas the mathematics for classical physics does not hold up.
Yeah.
So you actually get a different probability yield depending on how you look at the system. So it's not just an undetermined state, it's a superposition.
Yeah.
So this is really where this is one of the other experiments that kind of prove to people the truth of quantum mechanics.
Yeah.
You get different probabilities. It's not just some undetermined system or hidden variables.
And it's sort of checking but this was in the 70s, mind you. This was probably quantum mechanics at this point had already been so mathematically developed. So at this point, you had people like von Neumann, and Max Born, and Dirac was coming up, and people like that were at the foundation of this, and they had and Heisenberg. Heisenberg is unique in this picture because there was people like Schrodinger who absolutely hated. He said, I would be done. He said, I'm going to be done with quantum mechanics if we all agree that these are the results. He literally was like, fuck this. I don't want anything to do with quantum mechanics if this holds true.
And it's hilarious because Schrodinger is the one who made pretty much the ultimate formula for quantum mechanics.
Exactly. The Schrodinger equation. You can look this up as well. It works really well. Actually.
It's probably like, it's like almost like a magical formula to get your answer out for any kind of basic quantum mechanical system.
Yeah, if you've taken regular physics in high school, it's basically like F equals ma. For us.
A better thing to say would be it's like kinetic energy plus potential energy, because that's literally what the Schrodinger equation is. It's like a different equation it's like a quantum equation for energy.
Yeah, but for those who have taken just physics high school stuff. Yeah, it helps you solve.
It's as rudimentary as F equals ma.
Yeah, thank you.
That's better way to say it, probably.
Yeah.
So
he was upset, and so was Einstein. Einstein was so upset that he said, "Fuck it, I'm going to team up with two other physicists and try to think about something that sounds ridiculous." Because at this point, he had come up with special relativity. He was in his prime. He was like, he had BDE,
What is that?
He had big dick energy, he had this like confidence, like he could tackle this. He could finally sort of throw a wrench in there. So he came up with this thought experiment, the EPR experiment. Einstein, Podolsky, Rosen, paradox. Yeah.
Now you're gonna have to.
So I'll
refresh me on this one,
so
because
here we go.
I'm drawing a blank right now.
You know this. So I'll just to kind of get the wheels going or gears greased up. So what Einstein was trying to set out to do was he was trying to say, and this goes back to Bell, but what Einstein was upset about was he's like, you guys you guys are telling me that I can violate causality, because now if somebody does a cat in the box experiment over here, and I do a cat in the box experiment over there, these two things don't coincide. Like this, you're telling me one can happen before the other, and we'll get to this later, but
we'll
get into causality.
Why.
Yeah.
So the thing is, there's another quantum property that's very important. So we talked earlier about superposition. This is one of these quantum properties that distinguishes quantum from classical systems. Now, the quantum property that Juan is referencing here that has to do with the EPR paradox is entanglement. So you've probably heard of quantum entanglement. People talk about like quantum teleportation that has to do with entanglement.
Yes.
And basically what entanglement is saying is that you have two particles that are somehow
coupled
together.
Yeah.
So one is now intertwined or bound with another particle. It's never mind how that actually works.
Right.
It's a little bit more of like a detail that's kind of hard to explain.
Take that as a fact for now.
Yeah, and maybe we can explain it in a more understandable way on the next time we talk about quantum
for sure
information. But basically, just go with the fact that you can entangle two particles together and they're attached now. So basically what happens is, let's imagine...
Twins. Yeah, twins they're Siamese twins.
Sure.
They're bound surgically.
All right. No, so they're somehow intertwined. So what you can do is this. So Juan was mentioning earlier that you can violate causality.
How about this?
You might be saying, how is that possible? Go ahead, Juan.
Better example would be twins that are both twins, like literally twins that are born. Like say you know a pair of twins in your life, and they both feel when the other one is in pain.
Oh, okay, there
Something
you go.
Like that.
That little twin sense.
Yeah. So let's go with this
All
one.
right,
Yeah.
So let's imagine this then. Let's imagine these twin particles. One is on Earth, and the other one is
on the other side of the galaxy.
Yeah, sure, the other side of the galaxy. And let's say that's, of course, the other side of the galaxy is going to be several light years away, and everybody knows. Most people know, we won't say everybody knows, that nothing travels faster than light.
You've heard that, at least. You guys have had to have heard that.
A lot of people have heard it. But if you haven't, just take it as a fact. Einstein
Cosmic
also was responsible for this.
Right.
And that's kind of how he went into the whole relativity mathematics. But anyway, that's besides the point.
But that's what I'm saying. He came hot with special relativity. He was like, I got this fact.
Right.
This is in direct conflict with what you guys are reporting.
Yeah, so let's explain exactly what this is, though. What happens is you have twin A on Earth, and we've got twin B on the other side of the galaxy.
Yeah.
They're entangled, remember. When you actually measure twin A...
Let's say you pick him with a prick or something.
Yeah, so the thing is, when we say measure, we mean we're interacting with that twin somehow.
Yeah.
So you're interacting with A. What happens is instantaneously, twin B now
feels
that interaction.
Yeah.
And now they're locked into a state that is completely known by twin A. So let's say this. Let's come up with a good example. So let's say that let's use twins again. So humans. So twin A has his hand raised. Or twin A, you don't know what he's going to do yet. Twin B, you don't know what they're going to do either. They're entangled, though. So now let's say that twin A is on Earth again. Twin B is on the other side of the galaxy. You interact with twin A. He holds his hand up. If twin A holds his hand up, twin B automatically feels what twin A does, and he also holds his hand up. Yeah. So this is basically what these particles are doing in a sense. Yes. So twin A gets interacted with, he holds his hand up, twin B instantaneously knows that twin A holds his hand up, so therefore he holds his hand up too.
Yeah.
This is what particles are essentially doing on the subatomic scale.
Exactly. Yeah.
Instead of holding up hands, though, they are collapsing into like a spin state.
let's actually maybe I shouldn't have said that because that's a little bit.
Yeah. They have
going
certain
past what I
properties.
wanna
Let's say
do.
we're measuring certain things like
Yeah.
let's say this particle is blue and red. Or something.
Sure.
Yeah, one of them is blue and the other one's red.
Yeah.
In response.
So they just have some kind of instantaneous response.
Exactly.
So then what you can say.
Exactly.
So then what you can say is, oh, you can. What about this? What if I sent a message? So I could say, as soon as I want to send a message instantaneously using twin A. You know, if I interact with him, then I can send my message to twin B instantaneously across the galaxy. Yeah. The problem with that is now you're violating causality.
Yeah.
So the thing is, if you're violating causality, you're creating paradoxes, because this is where you get things like you could travel back in time to kill your grandfather.
Yeah.
This is what what happens when you violate causality.
Yeah, this is what Einstein was saying, like when he was like, this is nuts. Like you can't send information faster than light, but yet this information was being relayed to people through vast distances, you know.
Right. And distance is pretty much related to time, because space-time, what happens is the farther away you are, the longer it takes light to reach you.
Yeah.
So there's a causal relationship here.
Right. But here's the thing. So here's the thing. Einstein sort of was thinking at the time, this was Einstein's era at the time. And this is why he was the paper was kind of like, oh, you know, it doesn't really hold up, because in his paper, he assumed like, okay, twin A holds his hand up when he feels the pain. And then twin B, you know, it's going to take some time. Let's say that they for some reason have a telescope and you can see through the other side of the galaxy.
Yeah.
Your other twin raising his hand almost instantaneously. Einstein's argument was that, you know, it's going to take time for the light to travel.
Right.
But yet they somehow feel that. And he just could not coincide with that.
Right. Because you could see, like, if like what you're saying is, let's imagine that twin B had a telescope all the way to twin A.
Yeah.
He would never even see twin A raising his hand.
Yeah.
He would just raise his hand because he felt it.
Yeah.
And that's violating causality now. So you've messed up causality somehow.
Yeah, and that fucked Einstein up.
Yeah. But then what people realized is later on is that you actually cannot transmit information that way. So we've been kind of switching our understanding of quantum by looking at it as information transfer.
Yes.
So you actually cannot send information instantaneously.
Yes.
And you guys can try to think of ways that you can send a message instantaneously. Yeah. I've tried and I've thought many times, and you really can't. I can't think of any way.
And
you
the
can
fastest
send
thing is light, right? Theoretically, the fastest thing, the way you can send messages is light.
Right.
So
you cannot send an actual message that contains some kind of information instantaneously using entanglement. Come up with a scenario if you want. You know, if you leave a comment,
probably win a Nobel Prize if that's the case.
if you come up with something, leave a comment and we'll respond back to you. But
and we'll
I've
take
tried
credit for it.
Yeah,
and
I've
we'll
not been
publish
able to
a
come
paper.
up with something. But yeah, if you could somehow instantaneously transmit information, then you'd violate causality.
Yeah.
And then all kinds of hell breaks loose.
Yeah. And then Bell, we go back to Bell for this, but yeah, he actually showed that we have a non-local universe. Bell actually
can you
said
explain what non-local means?
So non-local means is that like those twins, that happens to those twins. That can happen. That physics does happen.
Yeah.
Yeah. Like,
but what's the distinction between that and local?
Meaning local, meaning that they are within a light years. You can send that information like they're within sort of a light years distance or something.
Yeah.
Like
they're in the boundary of
information where you can can affect
of where
them.
you can send information.
Yeah.
So once you're outside that boundary of past being able to send, or where you're outside of that light year boundary, I guess, like you're saying, then you're kind of in a non-local region.
Yeah.
It's a little deeper than that, and non-local is like a reserved term. It actually means something very specific in physics
and more technical. Yes.
So it's kind of hard to get into it now, but that's kind of the idea.
Yeah. Bell came through and was like, yeah, the universe is non-local, and what? Like it's like a drop the mic moment for quantum mechanics, because it had another bullet in its case.
Right.
You know,
and Einstein was thinking this was going to be it. Like, this is going to be disprove it. No, sir.
Yeah, man, it was wild. But yeah, so shit. I mean,
Yeah.
So where are we now? Where's quantum mechanics?
So quantum mechanics now is everywhere. So your phones use quantum mechanics. I mean, we're rocking quantum everywhere. Your computer's got quantum mechanics. A lot of it has to do with our nanotech and small technologies
And engineering and whatnot.
Yeah. So like, you know how the computer hard drives get smaller, or computer chips get smaller every, so few years.
Yeah.
We're at the quantum scale now, where quantum effects matter.
Yeah, and if it wasn't for De Broglie, actually, you wouldn't have things like electron microscopes, which give us high resolution images of objects
that we cannot see
that we couldn't do with a
microscope.
Light. Yeah, we couldn't do it with regular light.
Right.
We have to invoke light that has, electrons that have mass, and we can use
like if
De
you see
Broglie.
those crazy pictures of like tardigrades, have you seen those?
Yeah,
those are made with electron microscopes.
Yeah,
they look really crazy, and like they color them with really crazy neon colors and things.
Yeah.
And you can see like pictures of dust mites. Those are made with electron microscopes. Yeah. So they aren't using light; they're actually using electrons to image something.
Yeah. By tuning that, using that basic, De Broglie equation.
Yeah.
The basic wave equation, and just to be able to map life and biology and stuff. That's a feat on its own, and you also get things like probably like X-ray. You probably fine tune other things like, we can see X-rays. We can generate these waves.
Mm-hmm.
So there's these forms, different forms of light.
Yeah. So and we're figuring out quantum mechanics more and more these days.
Well,
it's
nowadays,
probably one of the most successful theories.
Well, here's the problem. Nowadays, we're kind of debating on what it means.
Right, the philosophy behind it.
We're debating the philosophy. There's physicists that have just gone on to try to have different interpretations of the physics, right?
Yeah.
Like for one, Terrence, I think you're probably one of those people that really aren't satisfied.
Yeah, I'm pretty unsatisfied with the explanations in mainstream.
Yeah.
The one that really irks me is the whole superposition is a mixture of 0 and 1 states.
Yeah.
I'm really have a pet peeve for people who describe quantum mechanics using math. Mm-hmm. But the problem is the only real way to describe things quantum mechanically is using math.
Because we have no view. We cannot, like, this goes back to the collapse issue, where we destroy the collapse, so to say, is to destroy the state or destroying the system. And I think I gave an example of, like, classically you can sort of think about you're using a bowling ball, when you're going bowling.
Yeah.
You can, classically, right? You roll the bowling ball, you hit one of those pins. Let's say you have a robot's level of precision and accuracy. You could probably hit the ball a pin perfectly. But in quantum mechanics...
What are you trying to describe? The measurement phenomenon?
Yeah.
Okay, yeah. So the reason why observing a particle, that's an annoying one that happens a lot too. People talk about observing a particle, the particle knows that it needs to be a particle now.
Oh, that's a whole nother issue, actually.
So it's really not the particle knows anything. Yeah. It's the fact that when you observe a particle, quote unquote, observing means you're interacting with it.
Yeah.
So the way we observe things and interact with objects is by shooting other particles at them.
Yeah.
Your eyes
taking light.
Are taking in light. So they're interacting with particles by exchanging photons.
Yeah.
So you're always shooting some kind of particle at something to interact with it.
Yeah. And this happens in the lab. Right.
And the thing is, photons are on the same scale as electrons in terms of they
energy
actually
exchange.
affect them. The same energy scales.
Yeah.
So when you hit an electron with a photon, you're actually imparting momentum to that photon or to that electron. So it's not like it just doesn't feel it. It actually feels that push. Yeah. And then it actually makes the particle go in a certain direction. So now it changes. It's locked into a particle state.
Yeah. It's no longer in its natural state. Its natural state.
Well, it's no longer in its wave-like state.
Right. It's no longer, in the state that it was, you were trying to observe it in, you destroyed it. You basically, in interacting with it.
They call it collapsing the wave function.
Yeah, they call it collapsing. Physicists call it collapsing, but it's really, you're interacting with it and you're destroying the system's initial state. So to say.
And I think English is still not even going to be able to do this one justice either, because when you're analyzing quantum things, you kind of just have to know the properties of the quantum object.
Exactly.
It's really, really difficult to try to explain it, because every time we explain things, you're explaining it from a Newtonian classical physics framework, which is the world that we reside in. You know, if we were quantum people, you know, who lived in the quantum world, then it might be easy to explain.
Yeah.
But the fact is, we're always trying to assert a classical viewpoint onto a quantum system. So your vocabulary always breaks down. And this is the problem that happens with a lot of things with quantum. You just cannot explain it in a way that makes sense with English. So the best way to do it is with mathematics.
Yes. Because you remove a lot of ambiguity. You remove, you know, and that's kind of the conundrum too. Like that's why you get these interpretations, because I think a lot of it is unsatisfactory to a lot of people intuitively, right?
Yeah. And that's a problem though, because people, when they interpret quantum, you know, they try to interpret actually what it is.
Yeah.
That's when you get really into misleading territory.
Yeah.
You know, I've had so many problems with quantum mechanics that from listening to pop sci culture talk about it instilled a kind of false framework for me to analyze things. And it's actually led to me interpreting things wrongly. Yeah. Because I'm using that pop sci interpretation.
Yeah. Same
you should
here.
always be falling back on the math if you want to do quantum mechanical operations, or try to understand some kind of quantum mechanical system. Do the math.
Because unfortunately, the math actually helps. It works. Like, we can really look back at it and say, shit, this is the thing that works. And we unfortunately have to sort of rely on the math to kind of give us some glimpse of what's going on. Here's the thing. I had a professor actually who did not think that the quantum world was like the math is. He said, I have no clue. We have no clue. The math just works. Yeah. And that's all he could say about it.
Yeah. That's all you really can say. I think that's the most responsible way too. Yeah. Like, I think physicists who try to interpret too much into quantum mechanics are doing a disservice. You know, I know people want to explain it to the layman and to general public, but what you say is the math tells us that we can do X, Y, and Z. You know, whether this is the actual way it happens, who knows? Just describe the properties of the quantum system. Don't try to give it meaning or interpretation from a classical sense or from a classical standpoint.
Beautifully put.
Thank you.
Yeah. So with that, I don't know. Did we hit all the points? I don't know.
I think so, man. I think that's a good primer. So, you guys, the follow up to this episode will hopefully be the quantum information episode, where we'll get into more of talking about quantum computing. You know, how you can actually make a quantum system. But it may not be the next episode. But it will be in the future. Yeah. We're working on it.
You can also look at, well, if you want, you can also sort of let us know in the comments if you'd want to see maybe some of the different interpretations out there that physicists have come up with. Because I'm going to let you know right now, Schrodinger tried to come up with his own interpretation. Right. De Broglie even had his own interpretation. Because he also was not satisfied with the, like, particle wave duality kind of thing.
I think we even have philosophers working on this.
Yeah, we do. Yeah. So philosophers have to come in and sort of ground, you know, the work, and even physicists have had to go into philosophy to try to go into the metaphysics, you know, because that's really what we're talking about. Right. Metaphysics. We are at this point.
So don't think that physicists know everything. The thing is, the math is really, really solid. Yes. But
it gives us good results.
Right. Yeah. And it works. Yeah, it works. And the thing is, and it's very predictive also, which is a really critical part. It predicts things. But the thing is, the understanding and the actual why it's happening or what is happening, that is not known. So that is leading edge stuff, and that's metaphysical, pretty much like Juan is saying. It could be metaphysical. There could be a way to understand it, but as of now, no one really understands it.
Right now, we're living by the words of von Neumann, you know.
What's that?
Shut up and calculate.
Exactly. This is an appropriate situation with quantum, pretty much.
So, yeah. So with that, you know.
You know, I'm not a fan of that saying usually, but for quantum, you pretty much have to, unfortunately.
Yeah, unfortunately, it is true because a lot of us, you know, for me at least, I came into physics absolutely enamored with quantum mechanics.
Yeah.
Just so taken aback by like this thing that makes everything up. So yeah, I was a little bit saddened in my undergraduate when they're like, shut up and calculate.
Right. You can't really think about it.
Yeah. I mean, not until you're given some leisure time, and it takes, honestly, at this point, there are retirement physicists who are trying to still think about these things in a more deeper level and try to understand the foundations of quantum mechanics. This is why Bell came in. You know, this is how he came up with this Bell inequality theorem, Bell's theorem, if you want to look it up. And yeah, I think we need more of that. I think we do need to probe the foundations of quantum mechanics, or the fundamentals, a little bit.
Now, Juan, do you think we're ready yet? Or do you think we still have more shut up and calculating to do?
I don't know. I think we know enough. You and I'm saying, are we? You're saying
I'm talking about
the field.
Physics community. Are we ready to start interpreting, or are we still on shut up and calculate level?
I think unfortunately, a lot of the funding schemes and incentives don't lend to the let's try to explain the world a little bit better.
True.
It's more about what's the biggest. Give me something that the public will really see an application to. Because it's public money. People want to see, the public funding wants to see their investment, a return on their investment.
They need flat screens.
Thank you. Yeah, they need flat screens. Look, flat screens are beautiful. This is amazing technology, but
right. At
the same time, physicists are still sort of philosophers with analytical tools. You know, we like to understand. We got this. A lot of us got into this because we want to understand the world we live in at a deeper level.
Right. But I think certain regimes lend itself better to philosophy. I think we can be more philosophers at the grand scale.
Yeah.
Like if you do relativity and things like that.
Right.
Or if you do classical physics stuff.
Yeah.
But in the quantum realm, I think that's more of the people who are shut up in calculators.
Yeah.
Because that's what it lends itself to.
Yeah.
It's so outside of our intuition.
Exactly.
Even though relativity is too,
It's also,
but you can still kind of conceptualize it with spaces and geometry and things, which are natural to us in the Newtonian scale.
Yeah, exactly. Yeah.
Yeah, man. So, any final thoughts, Juan?
No, I mean, I hope you guys stuck around, because this is really a primer and motivation into, going into quantum information. And if you guys like, we can talk a little bit more about the different kinds of interpretations out there, people that are trying to rationalize quantum mechanics in a more how would you say, holistic or comprehensive worldview that makes sense to us. So yeah, let us know. And fuck it, maybe if you don't let us know, we'll still do it anyway. I don't know.
Sounds good, man.
But yeah, with that, signing off. It's me, been your host.
Oh yeah, we didn't say our names again. God damn it.
No, we'll front load it. We'll front load it.
Yeah.
But once again, this is me. Juan, aka JJ.
He wanted to say that so bad.
Yeah.
And it's me, Terrence.
AKA Black, what do they call you?
Black Socrates.
Black Socrates, thank you.
I'll take it.
So with that, we're signing off, yo. Peace.
All right.
Yo, official outro to the Eigenbros.
He's aggressive.
Yeah. Hopefully, thank you for actually staying this long. We just want to let you know to visit our social media sites, Twitter.
Yep, at Eigenbros.
At Eigenbros.
So make sure you all subscribe to the channel.
Yeah.
Make sure you can check out the audio. It's going to be on Google Play, Apple, Spotify, any of those major platforms. Yeah.
And if you're on iTunes, please give us a review. That actually helps a lot, more than you would think. But yeah, like, comment, and subscribe. All the things people say.
I don't know what that means to play us out. What does that mean? To end the show?